This is Senior Algebra, Section 3.1. Today we're looking at graphing and linear equations with two variables. So take a look at what we're going to do today. We're going to write the solution as an ordered pair. We're going to do a little bit of graphing with x's and y's plotting points. So the first thing we're going to take a look at is linear equations in two variables, some different forms that we have. So the first one, ax plus by equals c, that's standard form. We use standard form when solving systems of equations algebraically using elimination. It's also a nice way to find x and y intercepts easily. The a, b, and c are simply integers. X and y are my variables. So an example, 3x plus 5y equals negative 8. We'll look at this a little bit more later. Slope-intercept form. This is the form you're probably most familiar with. Now there's a couple ways we can write it. We can write it as y equals a plus bx. Or more traditionally, you may have seen it as y equals mx plus b. Either way, I don't care how you remember it or what you think, which one you use, doesn't matter to me. But we do have to recognize a couple of things. The number in front of x, that is my slope, and the other number is my y-intercept. So an example is 6 plus 2x. So b, the number in front of x, that's my slope, or in the other one, it's m, whatever you want. And a would be my y-intercept. So in that example, 6 is my y-intercept, 2 is my slope. The next one, point-slope form. Point-slope form, we kind of use point-slope form as a go-between. It's usually something that when I'm given a point and given the slope, I can write it and then change it into something else. I can either change it into standard form or change it into slope-intercept form. I don't use it much for graphing, and I don't use it much to solve algebraically. So in point-slope, I'm given a point and a slope. The point is x1 and y1. The y and the x are my variables, and then the slope is b there. So taking a look at example 1 here, says decide whether each order pair is a solution to the equation. So we've done stuff like this before. This was one variable. Today we're doing two variables. Remember, we have x comma y. X comes first, then y, just like in the alphabet here. So I'm going to plug in 3 for x, 2 for y, 3 times 2 there, and I get equal to 12. So I get 6 plus 6 equals 12. We all know that's 12 equals 12. Now, what do I get? I get a true statement. So what does that mean? That means that 3, 2 is a solution to the equation. I'm going to do the same thing with negative 2, negative 7. I'm going to plug in to the original equation. That equation is in standard form. So it's 2 parentheses, negative 2. Close the parentheses, plus 3, negative 7, equals 12. I do a little multiplying here. 2 times negative 2 is negative 4. 3 and negative 7 is negative 21. When I add negative 4 and negative 21 together, or 4 negative 4 minus 21, I get negative 25. We know that is not equal to 12, so what can we say? We can say that negative 2, negative 7 is not a solution. Does that mean that 3, 2 is the only solution? No, just that negative 2, negative 7 is not a solution. In example 2, we're given the equation. Now we have to find the other coordinate here. So in A, I'm given that x is 7. I need to figure out what y is. So I'm going to plug in y equals 4x plus 5, and wherever there's an x, I'm going to plug in 7. 7 and 4 gives me 28. 28 and 5 gives me 33. So my point is going to be 7 comma 33. When I put in a 7, I get out a 33, kind of the input-output idea. In B here, now in B I'm given y. So I'm looking for x. So wherever there's a y, I'm going to put in negative 3. 4x plus 5. From here I solve it. Subtract 5, I get negative 8 equals 4x. And then I divide by 4, divide by 4. Whatever I do to one side, I do to the other. So I get x equals negative 2. So my solution would be negative 2, comma, negative 3. We're going to skip the next one just for a second here. We'll plot those in a minute. But first we want to talk a little bit about the graph here and plotting. So some things that we want. The origin is at 0, 0. That's where we start our graph here. And we have different coordinates here in different quadrants, they're called. The first quadrant is in the upper right hand corner, second quadrant, third and fourth. We go counterclockwise, meaning the opposite of the way a clock would usually go. In the first quadrant, we have our x comma y. The x's are positive, so if I started at 0 and went to the right, I would go positive, and going up I would be positive as well. In the second quadrant, I am negative for the x, and the y's are positive. In the third quadrant, x's are negative, so I'm going to go to the left, and I go down, which is negative. And in the fourth quadrant, to the right, that's positive, but down is negative here. So that gives me, in the first quadrant, x and y are both positive. Second quadrant, x is negative, y is positive here. Remember, I have the x-axis and the y-axis. So at this point now I'm going to take and plot these points. Take a second, copy them down. So remember, with plotting points here, I start with 1 and 5. The 1 is the x, the 5 is the y. So starting at 0, 0, I'm going to go 1 to the right, 1 in the x direction, and I'm going to go 5 up. So 2, 3, 4, 5. So I get up to 5. That is my A point. In B, I'm going to do the same thing. So I'm going to take my point, and I'm going to count how much in the x direction, how much in the y direction. That's my point B. In C, it's negative 4, negative 6. So I'm going to start at 0, 0. Eventually. There we go. Start at 0, 0. And I'm going to go negative 4 in the x direction, and then negative 6 in the y direction. So that's my point C. D, 3, 0. I'm going to go 3 in the x direction and 0 in the y direction. E, 3 halves. Now 3 halves, what is it? That's 1.5, so 1.5. And then I'm going to go in my y. So I'm going to go down 3. That's my E. If you haven't noticed already, F and G are the same. My bad. So F is 0, negative 4. I go left and right 0, I go down 4 for F. G you can just cross out. So I'm looking at the quadrants now. Which quadrant is A in? So 1, 5, 1 to the right, 5 up. That's in the first quadrant. B, the second quadrant. C is in the third quadrant. D, now it's not really in a quadrant, so we're going to say where it is located. It's located on the x-axis. So if it says state the quadrant and it's located on an axis, state that. E is in the fourth quadrant, and F is on the y-axis. So that's what the graph should look like there, plotting those points here. In example 4, it says the number of twin births in the United States has increased steadily in recent years. The annual number of twin births from 1998 to 2003 can be closely approximated by the linear equation y equals 3.563x minus 7.007.7, where x is the year and y is the number of twin births in thousands. So in A, it says find the number of twin births in 1998. 1998 is my x, so I'm going to plug in 1998 for x. Yeah, let's plug in x there. Yeah, that's a little bit better. So I'm going to plug in 1998, and then I'm just going to figure out. So y equals 100 and 11.174. I'm going to do the same thing for 2003. Plug in the 2003 right away this time, and then solve for y. So go ahead, multiply it by 2008, subtract 7,007.7, and I get for y 128.989. So if I was looking around a little bit, I would say approximately 111,000 and approximately 129,000. Again, we're not too concerned with where we're rounding at this point. And again, remember, we are 129,000 twin births. In B, it says, in what year were there about 118,000 twin births? So, in this one, I'm going to put 118 into the equation. Remember, the equation was y equals 3.563 minus 7007.7. Now, what does 118 stand for? That was a twin birth. So was that x or y? That was, in this case, y. So I'm going to plug it in for y, and I'm going to solve for x, the year. I'm going to go through it. I'm going to add 7,007 to both sides. I'm then going to divide by 3.563. So I get x is 1999.9. So what could we say? Well, 915. Still in the year 1999. So we could say 1999, or you could say 2000. We'll take a look at the graph in a little bit and see which would kind of be a better approximation here. So in C, I'm going to plot these 3 points that I had. 1998, comma 111, 2003, comma 129, and 1999 and 118. Now again, we'll take a look at the 1999, because it's 1999.9. It's pretty close to 2000. We'll see which would be a better choice there. So I'm going to plot the points here. One thing I am going to do is I'm going to get rid of that and get it down to 0 for my x and y axis there. I make the little squiggly lines signifying that the interval is not the same. Notice I'm counting on my y's and counting by 5s, but obviously I can't go from 105 to 0 in one swoop. So I use that little squiggly line to signify that. So the first ones I put in, 1998, 111, and the 2003. The next one, if I put in 1999 and that, I get a point right up here. If I put in 1999.9, or about 2000, I get a point right about there. We're going to find that the red is going to be a better approximation to it. So, in D, it says, looking at the graph, estimate how many twin births there were in 2002. So I made a little dotted line there between that, kind of our line of best fit. And I'm going to look at 2002. So in 2002, there's about 126, maybe 127, I guess. Again, that's 1,000. So 126 or 127,000 births. In E, it says algebraically determine what the answer would be. So I take the equation y equals 3.563x minus 7,007.7. I'm going to plug in 2002, and then I'm going to solve for y here. When I do that, I get y is equal to 125.426. So fairly close, about 1,000 off there. It's about 125,000. Notice here, if I made my line a little bit better here, notice how it goes, kind of goes through the top here. This is probably a little bit of an overestimation. If I went it through kind of the center, it'd probably get a little bit closer to the 125 mark. So again, we're estimating, because we're looking at the graph, it's not as precise as we can be as if we were doing it algebraically there. Hope everybody did well on the test today, and I hope you have a nice 3-day weekend.